At least while it's morning for me, whatever time you're actually watching this, who knows? But anyways, I was feeling a little Beatles. All right, so let's get into this. So I'm going to start here on our chapter 5 on gas laws. Okay, so maybe some of you might have some familiarity with this from some previous chemistry courses. But if not, that's okay. We're starting from the beginning. Okay, so we start by noting that the definition of pressure, not what you're experiencing now, being a college student in the year 2020 with a pandemic and forest fires, right? Pressure, as related to gases, is by definition force over area. So a force acting over an area. Okay, and the proper, what I'll call, our SI unit, our standard, or the system international unit, is the Pascal. So that's a named unit that's named after a person, Pascal. And by definition, a Pascal is 1 Newton per square meter. So a Newton is a unit of force, and a square meter is a unit of an area. So that gives us a Pascal. Something you might be more familiar with is the pound per square inch, the PSI, right? So that is 1 pound of force per square inch, okay? And it's important to note here, so atmospheric pressure, what we experience at sea level, so right, 1 atm, so we'll say at sea level, okay, assuming there's no weather systems changing the pressure, that's the same thing as 14.7 pounds acting over a 1 square inch area, okay? In terms of pascals, that's also the same as this crazy number, 1.01325 times 10 to the 5th pascals, or that's the same as 101 kilopascals. So I take this number and divide it by 1,000, right? I can still do all of my scientific notation stuff. So about 100 kilopascals is 1 atmosphere. Okay, so what about all these other units? Well, there's a really famous device here. This is called a barometer, a barometer, okay? And this was actually invented by a gentleman of the name Torricelli, an Italian scientist who was Galileo's graduate student. Pretty cool stuff. So we have this thing called the barometer, invented by Torricelli. And the idea of this device is you have this pool containing liquid mercury, and atmospheric pressure is pushing on that liquid pool just like it's always pushing on everything all the time. And you have this inverted tube. So if I draw like a cross section of this, right, here's that liquid, and the tube is all the way down in the bottom of that liquid, okay? And as the atmosphere pushes on this liquid, you notice here that it's evacuated, so there's vacuum between the top of the tube and the rest of the liquid. And so what that in turn, the atmosphere pushing on this liquid, forces the liquid to rise up that column, okay? And as it turns out, at sea level, at exactly 1 atmosphere, the height of this column will always be the same. Of course, that's at exactly atmospheric pressure. And as it turns out, the height of that column of mercury is 766 millimeters. Now, it's important to note, if that were a different liquid, if it were water, for example, it would be much taller. If this were water, it would actually be closer to like 13 meters, like a full 1-story house. And that's due to the difference in the density of water versus mercury. So mercury is very dense, so that's why this only goes up 760 millimeters. So we call that measurement, 1 atmosphere, 766 millimeters of mercury, we call that 766 torr, for Torricelli himself. And if you're kind of a weather buff, if you're into looking at like pressure and what's going on and with atmospheric conditions, you will also know that that number, 766 millimeters of mercury, is the same as 29.92 inches. So that's just converting an inch to a meter, or excuse me, converting a millimeter to an inch rather, okay? So all of these units, I'm not going to make you memorize. You'll be given them. But you do need to be able to interconvert pressure units back and forth. Okay. So for example, suppose on one day we find that it's 0.956 ATM, right? Let's say there's a low pressure system out there, there's a storm, and we see that it's 0.956 atmospheres. How many torr would that be? Well, look, we can do the same thing where I apply my dimensional analysis skills, and I know from this chart, 1 atmosphere is 766 torr. Okay, so on a day, you know, where there's slightly less atmospheric pressure, oops, I got a calculator right here. So I can say 0.956 times 760. And on that particular day, it would be, you know, with 3 sig figs, let's say, 727 torr, for example. Okay, so be able to use any of these types of conversions in the same way that we've been doing. Okay, you don't have to memorize these units, but you should have some amount of familiarity with them. Okay, so let's move on. So what exactly? Oh my God, you know what I just noticed? I've been skipping my whole first slide this whole time. That's okay, I'm not re-recording it. All right, so all this stuff applies. This barometer, Torricelli. What I wanted to tell you first, I realized something about that was off. What exactly is atmospheric pressure in terms of something that we're familiar with? Well, as it turns out, our atmosphere is really, really thin in comparison to the size of our planet. Right, it's only about 50 kilometers thin, but our planet's circumference is about 40,000 kilometers. So the atmosphere is really, really thin. And if there's a ginormous area, right, 5 times 10 to the 14 meters squared. Well, as it turns out, the mass of our entire atmosphere, even though it's really thin, it's quite massive, 10 to the 18 kilograms. And what's keeping that pressure down is gravity. Right? This is a massive amount of force, right? Force due to gravity being exerted on us all of the time. Gilbert, the author of our book, did a really cool calculation and said the equivalent force of this, the equivalent force of the atmosphere is if you took your hand out like this picture is showing, and I've lost track of how many books there are here, but this is accurate. This is accurate for the force due to the atmosphere. This number of books balanced on your single hand, right? The square area, the surface area of my hand, and the mass of all of those books. So to me, what's always impressive about this kind of scale is it shows us that our bodies are quite strong, right? We have this atmospheric pressure being exerted on us all the time. We evolved this way, okay? That's why as humans, we're actually quite sensitive to very small changes in weather or atmospheric pressure. You might have a family member that has an injury who can tell when a storm is coming, right? Because there might be a change in atmospheric pressure and they feel it in their joints. That's not an old wives' tale. That's for real. We've come accustomed to being quite sensitive to changes in atmospheric pressure. So this was the first slide I was supposed to do. Then I was going to tell you about all these numbers and units. C'est la vie. We did them both. Okay. So let's move on. So now I want to talk about another type of device, very similar to a barometer, but it's just slightly different in its construction, a manometer. Okay. And so there's 2 ways that we can use a manometer to measure pressure. One in which we have greater than atmospheric pressure. Okay, so in this case, you know, perhaps you have a sample, and I'll say the pressure of the sample is greater than the pressure of the atmosphere. So then in that case, this tube, right in the barometer that was closed and it was evacuated, so this tube would be open, okay? And the atmosphere pushes on this liquid level, and when this is all closed, and this is what makes this a manometer, by the way, because it's not measuring atmospheric pressure, it's measuring the pressure of the sample. Barometers measure atmospheric pressure, manometers measure pressure of a gas sample, okay? And so now what happens is as soon as you open the sample, you've got the sample pushing on the liquid level, but the atmosphere is also pushing on the liquid level. And of course, if the pressure of the sample is greater than the pressure of the atmosphere, it will displace the liquid in this U-tube. And this delta H, that difference in height, will give you what the actual pressure is. Because once again, we know that the pressure of the atmosphere is supposed to be 766 millimeters of mercury. Okay, we measure whatever that is, and then the difference gives us the pressure of the sample. Okay, great. So now what if we have less than atmospheric pressure? Well, we can still use this manometer, but now this end is closed. Okay, and so now there's no force opposing this thing, like in the atmosphere. Okay, and so let's just let me write this down really quick. P sample is less than P ATM. And so now when you open this up, okay, what ends up happening is there was actually some slight amount of pressure in there, as well as in there. But now when this opens, okay, all of that pressure gets sucked in to the sample. And as you can see, that reduces the height of that. And then the height, the change in this height only gives you the pressure of the sample in that case. Okay? So moving on. So now, as a reminder, when we do stuff with gases, we are going to primarily use the Kelvin scale. We will occasionally have some, some problems that have centigrade, that have Celsius in them, but we will predominantly use the Kelvin scale. So this is just a reminder. I do want you to commit to memory the conversion of Celsius to Kelvin or Kelvin to Celsius. So remember this equation. I'm just kind of backing up and going to our pressure units. You don't have to memorize any of these, okay? These will be given to you, okay? So moving forward. So I want to briefly talk about all of the various gas laws. I have some video demonstrations. This is normally where I do some of these demos in the lecture hall, and I love doing these demos, but I don't have access to a vacuum chamber or liquid nitrogen at my house, unfortunately. Okay? And after I summarize all of these gas laws, then that'll be the end of this first video. So the first one I want to talk about is Boyles Law, and you should be familiar with all of these laws by name and by their relation. Okay? So Boyles Law says that pressure and volume, so the pressure and volume of a gas sample are inversely proportional to each other. Okay? So this little crazy fish looking thing, so this means proportional to. Okay? And so what that means, if we looked at a graph of pressure versus volume, and what's also important to note, this is at constant temperature, okay? So assuming that we can hold the temperature of our gas sample fixed, like suppose it's a balloon filled with some air, if I decrease the pressure around the balloon, so in other words, if I decrease the pressure, notice what happens. The volume has to increase, okay? But what if I increase the pressure surrounding the balloon? Like I squeeze the hell out of that balloon, right? Well, it's going to get smaller, okay? And so that's what we see in this graph. That's what this relationship means. P is inversely proportional to 1 over V, okay? Another thing we could do with this Boyles Law, we could do algebra with this. And if I multiply both sides by V, that cancels this V. And now I have PV. Okay, but in the same way with our dilution equation, right? P at condition 1 times V at condition 1 has to be P at condition 2 times V at condition 2. So in other words, if I have a balloon, let's say it's, rather small. Here's my balloon, and I've got P1 and V1. So I've got a volume of the balloon, and there's some pressure all around this balloon, okay? Suppose now that P1 is less than P2. What's going to happen to the volume of this balloon? It's actually going to get bigger. It's going to get much bigger, depending on, of course, how different P2 is. And I've got a cool video of that to show you here. Let's see. It's hidden back here, and let's put it in the little view. Oh, you guys, this is so meta. I'm making a YouTube video
in a demonstration of Boyles
while
Law,
I'm playing you
we'll
YouTube
place a
videos.
balloon in a vacuum bell jar. We'll apply a vacuum, which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyles Law,
The PEEP. This is the best chemistry demo ever.
Jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the PEEP will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyles Law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
Okay, that was cool. I would not want to make my vacuum chamber all messy with shaving cream, but I'm glad that that person did it. Okay. Okay, so Boyles Law, P and V inversely proportional. If I squeeze on a sample of gas at constant temperature, its volume has to decrease. If I reduce the pressure around the volume at constant temperature, its volume has to increase. Okay? And really the reason for that, what's going on, is because there are also molecules in the balloon pushing the balloon out, right? So if this is like my P1 and this is my P2, eventually they want to have an equal force onto each other, right? This is related to Newton's second law. For every action, there's an equal and opposite reaction, okay? So this is why we see the balloon swelling or compressing depending on how the outside pressure changes, all right? So let's do a sample problem. So a balloon is filled with hydrogen at a pressure of 1.35 atmospheres and has a volume of 2.5 liters. If the temperature remains constant, what will the volume be when the pressure is increased to 2.5 atm? Okay, so we remember we're going to use this equation. P1V1 equals P2V2. It doesn't matter what I pick for 1 and 2 as long as it's consistent. And it's asking me for the volume, so then I'm going to say let's solve for V2. So I first like to do the algebra. And to isolate V2, I'm going to divide both sides by P2, okay, which will give me P1 times V1 divided by P2, and that all equals P2, okay? So now they tell me it's 1.35 atm, okay, times V1 is 2.54 liters, and then now what will the volume be when the pressure is increased to 2.5. Okay, so it's always good to kind of ask ourselves, do we expect the volume to get bigger or smaller? And if it's increasing the pressure or squeezing it, we're going to make it smaller. Okay, so let's do that simple math. 1.35 times 2.54 divided by 2.5, and with looks like 3 sig figs all around. Yep, it got smaller. 1.37 liters. Fantastic. Okay. Let's move on. And let's talk about Charles' Law. So another one of our named laws. I want you to know the name, and I want you to know the relationship. So Charles' Law says temperature and volume is directly proportional, but now this time at constant pressure. Okay? So again, our little, I always want to call it like the little Jesus fish, but it's like the proportionality sign, right? Volume is proportional to temperature. And again, I could also make an algebraic relationship out of this. V1 divided by T1 equals V2 divided by T2. And so because they are directly proportional, that means a graph of pressure versus temperature is just going to be a straight positive increasing line. So in other words, now if I have a sample, okay, and let's say I increase the temperature over that sample, of a gas, right? Then its pressure will increase, okay? And the reason for that, what's going on with that, if we look back to our balloon example again, okay? If I increase the temperature of these molecules, they start to get really excited. They're moving around like crazy. They're colliding with each other. They're colliding with the balloon. Okay? So as this gets hotter, right, it has to expand because the molecules are getting even more excited and pushing out the rest of the atmosphere. Conversely, if this thing gets colder, the molecules aren't as excited. Particularly, they're not as excited as the molecules surrounding the balloon, right? So they move slower, they're a little bit more lazy, and the molecules on the outside are able to squeeze them in. And of course, at constant temperature and volume, rather, okay, so right, so I was about to say when the pressure changes, the pressure is not changing, but what's happening is as the molecules are becoming less excited as they get colder, they don't occupy as big of a volume. Okay, so it's as if the pressure is squeezing them out, but it's really not. It's that they're not pushing away the balloon, or they're not pushing out the rest of the atmosphere as much because they're not as excited. Okay, and there's a really cool video to demonstrate this. I love this couple. They're really cute here. This little demo they put together. Okay, this is fun, and this is what I would do in the classroom as well if I were able.
No balloon.
Just science.
They're funny, right?
Hi, I'm Joanna.
And I'm Steve.
And this is a container of liquid nitrogen.
And this is a really big balloon.
Let's see what happens when we place the balloon in the liquid nitrogen.
Okay. Whoa, wait. Isn't the balloon gonna pop?
We'll see.
Oh, man.
Really cold, minus 200 Celsius. Kind of hilarious, right?
Huh. Okay, so the balloon didn't pop. There's obviously a hole in the balloon somewhere because the air's leaking. So maybe instead of popping, maybe the balloon just got really cold and it cracked like an egg, and all the air is slowly leaking out of the crack.
Well, if that's the case, what's the balloon going to do when I take it out?
Nothing. It's a balloon with a hole in it, and all the air's gone.
Well, I'd say the air is still in the balloon.
So where's the air?
She's right.
Right there.
That's water.
Nope. If that were water, it'd be frozen solid. That's liquid air.
What?
When we place the balloon in the liquid nitrogen, the air inside the balloon gets really cold. When particles of a gas get cold, they start to slow down and take up less space. If we can get the gas cold enough, we can change it from a gas to a liquid. That's what happened inside the balloon. We changed all the particles of nitrogen and oxygen to a liquid.
So how do I get my balloon back?
We just have to place it someplace hot, like the table.
Now all those molecules are warming up.
Now the reverse is happening. The heat from the table is making the liquid air inside boil. When liquid boils and changes to a gas, the particles move faster,
Okay, cool stuff. And so all of the steam that you saw, all of that fog, that was not the liquid nitrogen. That was actually water in the atmosphere. And that liquid nitrogen is so cold, right, minus 200 Celsius, that it actually freezes out the water that's in the air. Really fantastic, cool demo of Charles' Law there. So again, pressure and temperature, or excuse me, this is why I'm confusing myself, because this graph has got pressure and temperature. Temperature and volume. So if I put volume also on this axis, now I just realized why I was confusing myself there, okay? Temperature and volume, directly proportional, okay? So another sample calculation. A sample of methane gas that has a volume of 3.8 liters at 5 C is heated to 86 C at constant pressure. Calculate its new volume. Okay, so once again, I can use these proportionality equations. And because of the proportionality of these equations, I can leave these in degrees C. I don't have to turn them over to Kelvin. Eventually, we will have to turn our temperatures into Kelvin, and I'll tell you when, okay? So we're going to calculate its new volume, so let's make that V2. And I'm going to multiply both sides by T2, so I can isolate that variable. And now that's going to be T2 times V1 divided by T1 equals V2. Okay, so V1 is 3.8 liters. T1 was 5 degrees Celsius. And T2 is 86 degrees Celsius. So you can see that's why it doesn't matter what units I use for temperature in this equation, because they cancel. So 86 divided by 5 equals, and then times 3.8. That's some serious expansion, right? That's huge, okay? 65 liters to heat that thing up. That's major, okay? Pretty cool. Okay, so moving along. Okay, so now the last one I'm going to talk about is Harmon's law, okay? And Harmon's law says that pressure is directly proportional to temperature. Or in other words, P1 over T1 is equal to P2 over T2. So this graph, so somehow I copied and pasted two graphs onto my Charles' Law. So that's what happened here, okay? So, but it's similar to the other laws that we described, and it can be related to the fact that as these molecules change temperature, as they get hotter, they get more excited, okay? And so now this, of course, picture makes perfect sense, because for a fixed volume, right, this is a piece of glass. So it's not going to expand or contract like the balloon does. So as these molecules get hotter and they're pushing against that glass, the pressure has to increase, okay? And I think I have a sample problem of this, okay? I'm just going to check something really quick before I do this, because now I'm thinking about that whole Kelvin thing I just did, and something is not sitting right in my head. Yes, I knew I screwed it up. Kelvin. I should take my own advice. Okay, I should take my own advice. I knew that that volume seemed way too high. So I'm going to back it up. And we're just going to say Kelvin. Damn it, Harmon. More coffee. Okay. So Kelvin. Okay. So let's do that. Okay. I knew something wasn't sitting right. So 5 degrees turned into Kelvin is going to be 5 degrees C plus 273, and that equals 278 Kelvin. And then 86 plus 273 is 359 Kelvin. And yeah, this is going to be a much different answer. Something I think that's more logical. Okay, so 359 Kelvin. And then what do we say? V1 is 3.8 liters. And then now divided by 278 Kelvin. Yeah, we're going to get a bigger volume, but not like 65 liters. I knew that didn't seem right. Okay. So now and then times 3.8. Okay. 4.9 liters. That makes a lot more sense. Okay. I knew that thing could not get to 65 liters, and I went on to the next slide, and it's Monday. Okay. Kelvin. All the time. Kelvin. Gas laws. Kelvin. Do it. Now, we're going to use Kelvin for this calculation. Okay. So this is a fun problem. Labels on aerosol cans caution against incineration because the cans may explode when their internal pressure exceeds 3 atmospheres, 3 times atmospheric pressure. At what temperature in C will an aerosol can burst if the internal pressure inside the can is 2.2 atmospheres at 25 degrees Celsius? Okay, so let's back up. Well, what are we asking? Okay, at what temperature will an aerosol can burst if the initial pressure inside, and I'm just going to right away call that P1, is 2.2 atmospheres, at 25 C. So that means this T goes with this P. And I am going to turn that into Kelvin, but then I'm going to have to turn it back into Celsius to finish the problem. Okay? So 25 Celsius is 298 Kelvin, 25 plus 273. Okay? And now I'm going to say P2 equals 3.0 ATM, and I want to solve for T2. That's going to tell me at what temperature will this can burst. Okay? And let's remind ourselves, Boyles Law is P1 over T1 equals P2 over T2. So that's going to be, so I like to do the algebra first. I like to get the equations all arranged in the way that I want. So now I'm solving for T2. Okay? So I'm going to multiply both sides by T2. Okay, and that gives me T2 times P1 over T1 equals P2. And then now I'm going to multiply both sides by P1 over T1 to cancel these things. Let's see here. Excuse me. Let's back up for just 1 second. Okay. So I canceled the T2 and the T2, right? So now I've got T2 times P1 over T1 equals P2. So remember, I'm solving for T2. So now, yes, I'm going to multiply by T1 over P1, both sides. Okay? So that cancels my P and my T. And now I know T2 equals P2 times T1 over P1. And now my P2 is 3 atmospheres times my T1 is 298 Kelvin. And my P1 was 2.20 atmospheres. Okay, so when I do all of that, 3 times 298 divided by 2.2 equals, okay, so that's 406 Kelvin, but it's asking me for the answer in Celsius. So now I'm going to say minus 273. And that would be to the nearest 1 degree C, 133 degrees Celsius. Before that aerosol can will explode. Okay, moving on to the last named law that I'm going to discuss, and then that'll be the end of the video. Okay? So I think something's getting cut off right there. So the last one is Avogadro's law. And yes, that's the same Avogadro as Avogadro's number. And Avogadro says volume and moles are directly proportional when temperature and pressure are constant. All right? So now if you imagine our little balloon here, let's say we fill it with 1 mole of helium, and we have the temperature and pressure constant. If temperature and pressure remains constant, the only way I can get the balloon to become bigger is if I add more helium. Makes sense, right? And so on this scale, right, you can see V and N are directly proportional, okay? And so as you double the number of moles, you double the volume. If you triple the number of moles, you triple the volume, okay? So it's as simple as that. I'll summarize this very, very quickly, and then we're going to come back. I'm going to have a whole video on the ideal gas law. Okay. So when we take these laws, and I've left out Amontone's law, but if we take Boyles' law, Charles' law, and Avogadro's law, and combine all of these, right? These are all proportionalities. We get to the very famous ideal gas law. PV equals nRT. Okay, so pressure times volume equals the number of moles times temperature times this thing called the gas constant. Here are all of the various flavors of the gas constant, depending on what units you are. I will circle this one. This is the most common one we will use, 0.08206, because it's got now V in liters, pressure in atmosphere, temperature in Kelvin, and moles, and that's how you get this number, okay? And so this gas constant, this R, right, notice it changes this from being proportionality signs to equal signs. So that's what the constant does, is it takes these from being proportionalities to equalities, okay? And so now with this ideal gas law, PV equals nRT, we can calculate what's going to happen to our gas if any of these 4 things change. So notice in all those other laws, it was like, okay, Boyles' law, pressure is proportional, inversely proportional to volume if temperature is constant. Volume is directly proportional to temperature if pressure is constant. Volume is proportional to moles if pressure and temperature are constant. Well, in the ideal gas law, all of the things are free to change, okay? And so we're going to explore that more in the next videos. Okay, folks, I'll see you later.